Beneath the vast and uncharted depths of the ocean, an ancient and unstoppable force is stirring. It has remained silent for centuries, concealed beneath miles of crushing water pressure, hidden from the view of satellites and the reach of human exploration. But now, something has changed. Recent seismic readings have sent shockwaves through the scientific community. An enormous underwater volcano, long thought to be dormant, is showing alarming signs of activity. The tremors are becoming more frequent. Deep-sea thermal sensors are recording a steady increase in temperature. Strange, ominous plumes of gas are rising from the ocean floor, hinting at the immense pressure building beneath the Earth's crust. Something is happening beneath the waves, something we may not be prepared for. Volcanologists, geologists, and oceanographers have rushed to analyze the data, and the implications are as terrifying as they are fascinating. If this underwater volcano erupts with its full potential, the consequences could be devastating. The very fabric of the ocean floor could shift in an instant, unleashing a force so powerful that it could trigger one of nature's most feared phenomena, a mega-tsunami. A tsunami unlike any seen in modern history, capable of swallowing coastlines, leveling cities, and forever altering the map of the world. For those who study the Earth's volatile movements, this scenario is not just theoretical. The past holds chilling examples of the raw power of submarine volcanoes. The eruption of Krakatoa in 1883 generated a tsunami so massive it wiped out over 36,000 lives in a matter of hours. More recently, in 2022, the Hunga-Tonga-Hunga-Hapai eruption sent shockwaves around the globe, generating tsunamis that reached as far as Japan and South America. But what's happening now could be even more catastrophic. The sheer scale of this underwater volcano dwarfs those past events. And with its location near tectonic fault lines, the potential for widespread destruction is growing by the hour. The signs have been there for months: unexplained shifts in oceanic pressure, strange patterns in marine animal migration, and a sudden increase in minor tremors spreading outward from the volcano's location. At first, these anomalies were dismissed as natural fluctuations, but as the data continued to pour in, the truth became undeniable. We are witnessing the awakening of a geological giant, and with it, the possibility of a disaster that could shake the world. The question now is not just what will happen when this volcano erupts, but how prepared are we for the aftermath? How much time do we have before a wall of water, hundreds of feet high, comes crashing towards civilization? And perhaps the most haunting question of all, are we already too late to stop it? Deep beneath the Earth's surface, an unseen battle rages. It is a battle between immense geological forces, an ongoing struggle that has shaped the planet for billions of years. At the heart of this conflict lies the movement of tectonic plates, vast, continent-sized slabs of rock that make up the outer shell of our planet. They shift and grind against one another in an unceasing dance, driven by the intense heat of the Earth's mantle. And now, in the region where this massive underwater volcano is stirring, those tectonic forces may have reached a critical breaking point. The world's ocean floors are not as static as they seem. Beneath their depths, there are enormous rifts, gaping fractures in the Earth's crust where new land is constantly being formed. These rifts, known as mid-ocean ridges, are some of the most geologically active places on Earth. Magma from deep within the planet wells up through these cracks, creating new seafloor and pushing the existing crust outward. But this process is not uniform. In some regions, the movement is slow and steady. In others, the forces build up over centuries, until finally, something gives. When that happens, the energy release can be cataclysmic. In the case of this particular underwater volcano, scientists believe it sits near a zone of extreme tectonic stress, a subduction zone, where one plate is being forced beneath another. These zones are among the most volatile locations on Earth, responsible for some of the most powerful earthquakes and volcanic eruptions in history. When a subduction zone becomes unstable, the effects can be disastrous. The downward moving plate melts as it sinks into the hotter layers of the mantle, creating reservoirs of magma that can rise toward the surface with explosive force. If enough pressure builds up beneath the ocean floor, the result is an underwater eruption of unimaginable scale. To understand just how powerful these forces can be, one only needs to look at past events. In 2018, the eruption of Indonesia's Anak Krakatoa was triggered by shifts in the region's subduction zone. The eruption was violent, but what followed was even more devastating. The rapid displacement of land beneath the water caused a tsunami that swept across coastal areas, killing hundreds in a matter of minutes. And that was from a volcano far smaller than the one currently awakening. Now, seismologists are warning that the same scenario could be unfolding once again, but on a much larger scale. In recent months, an unusual cluster of deep-sea earthquakes has been detected near the site of the awakening volcano. These quakes are not the kind that shake cities and rattle windows. They are deep, slow-moving shifts in the Earth's crust, the kind that signal massive geological change is underway. The frequency and intensity of these tremors are increasing, suggesting that magma is rising toward the surface, breaking through layers of rock and searching for an escape. Even more alarming is the fact that these earthquakes are not isolated. They are part of a broader pattern, one that suggests a cascading effect. As one section of the tectonic plate moves, it triggers movement elsewhere. Scientists have observed similar patterns in the lead-up to major eruptions and mega-tsunamis in the past. The warning signs are clear, and if history is any guide, this situation is rapidly approaching a point of no return. But what makes this event even more dangerous is the sheer amount of water involved. Unlike land-based volcanoes, which erupt into open air, underwater volcanoes must fight against the immense pressure of the ocean. This pressure can hold back an eruption for a time, allowing heat and gases to build up far beyond what would be possible on land. When the eruption finally happens, the release of energy is far more violent. The water instantly flashes into steam, expanding with explosive force. In some cases, entire sections of the ocean floor can be displaced in an instant, triggering underwater landslides that send tsunamis racing across the ocean at speeds of over 500 miles per hour. The consequences of such an event would be felt across the globe. Coastal cities thousands of miles away could be at risk. Entire island nations could find themselves facing waves taller than skyscrapers. And all of it could happen with little to no warning. Unlike traditional earthquakes, which can be detected through ground-based sensors, deep-sea volcanic activity is far harder to monitor. By the time the eruption is confirmed, the waves may already be on their way. What we are witnessing now is the beginning of a sequence of events that could lead to one of the most significant natural disasters of the modern era. The tectonic forces beneath the ocean are shifting, magma is rising, and the balance that has kept this massive underwater volcano dormant for centuries is beginning to collapse. And this is just the first major factor in the equation. There is much more at play here, more forces conspiring to unleash this sleeping giant. What other elements are feeding into this event? And how much time do we have before the final, irreversible moment arrives? The signs of unrest beneath the ocean floor are becoming more pronounced, and scientists are racing to decode the warning signals. As this massive underwater volcano continues its awakening, one critical question remains unanswered. How much pressure is locked beneath its surface? And what happens when that pressure becomes too much for the Earth's crust to contain? Unlike surface volcanoes, where visual cues such as smoke plumes or lava flows provide early indicators of activity, underwater volcanoes are far more elusive. Their eruptions are often masked by the vast weight of the ocean, making them some of the least understood geological phenomena on the planet. However, recent technological advancements in seafloor mapping and remote sensing have allowed scientists to observe the hidden world beneath the waves with greater clarity than ever before. What they are seeing now is deeply concerning. Satellite-based measurements have revealed a subtle but significant bulging of the ocean floor in the region surrounding the awakening volcano. This uplift, often a precursor to volcanic eruptions, suggests that a massive chamber of magma is forcing its way toward the surface. The deformation of the seafloor is not limited to a single location but is occurring across a vast area, indicating that the magma reservoir beneath this volcano is not only immense but highly pressurized. The scale of this uplift is unprecedented. To put it into perspective, a similar event occurred prior to the 2011 eruption of the Nebro volcano in Eritrea. In the months leading up to that eruption, satellite imagery showed a slow but steady inflation of the ground surface. Scientists at the time underestimated the magnitude of the event, and when the eruption finally occurred, it sent an ash plume nearly 15 kilometers into the sky, disrupting air travel across the region. But that was a terrestrial event, one that could be observed and monitored. This underwater scenario is far more difficult to track, and the sheer volume of water involved makes it exponentially more dangerous. If the pressure beneath the seafloor continues to build without release, the outcome could be catastrophic. The trapped gases and molten rock within the magma chamber act like a ticking time bomb, waiting for a trigger. That trigger could come in the form of an earthquake, a sudden shift in the surrounding tectonic plates, or even the gradual weakening of the rock that currently holds everything in place. And then, there is another factor that cannot be ignored: the hydrothermal systems that exist around these deep-sea volcanoes. These systems, which spew superheated water and mineral-rich gases from the seafloor, are often a sign of intense volcanic activity. In normal conditions, they create unique deep-sea ecosystems, supporting life forms that thrive in extreme environments. But when a volcano enters a phase of heightened unrest, these hydrothermal vents can become conduits for massive bursts of steam and gas. Some researchers fear that if this volcano erupts with enough force, it could trigger what is known as a limnic eruption, a phenomenon in which superheated gas, such as carbon dioxide or methane, is suddenly released from the seafloor in a massive burst. This type of event has been observed in freshwater lakes, most notably at Lake Nyos in Cameroon, where a sudden release of CO2 in 1986 suffocated thousands of people and animals within minutes. If a similar event were to occur beneath the ocean, the rapid displacement of water and gas could add another unpredictable element to an already volatile situation. Another key concern is the composition of the magma itself. Not all eruptions are the same. Some produce slow-moving lava flows, while others generate explosive bursts of superheated ash and gas. The nature of this eruption will largely depend on the type of magma fueling it. If the magma is rich in silica, it will be highly viscous, trapping gases and building pressure to extreme levels before finally erupting in an explosion of unprecedented force. This is the kind of eruption that could send shockwaves across entire ocean basins, potentially displacing enough water to create a mega-tsunami capable of devastating coastlines around the world. And yet, despite the growing body of evidence pointing toward an impending eruption, there are still many unanswered questions. Could this volcano enter a prolonged phase of unrest without a full-scale eruption? Or is the process already too far along for that? Some scientists are turning to historical records for answers, looking for patterns in past underwater eruptions that might provide clues about what to expect. One event that is drawing particular attention is the 2022 eruption of the Tangahunga-Ha'apai volcano. This underwater explosion was so powerful that it generated atmospheric shockwaves that circled the globe multiple times, causing disturbances in air pressure thousands of miles away. The eruption sent an ash plume higher than any previously recorded, and the force of the blast displaced enough water to generate a massive tsunami that reached as far as South America. But the volcano now awakening is believed to be significantly larger than Tangahunga-Ha'apai. If it follows a similar pattern, the consequences could be far greater. The potential for a mega-tsunami is one of the greatest fears among oceanographers and disaster response teams. Depending on the scale of the eruption, the resulting waves could travel across entire ocean basins, reaching speeds of over 500 miles per hour. Coastal cities thousands of miles away could be at risk, with little to no time to prepare. As the signs of impending eruption continue to intensify, scientists are scrambling to deploy more monitoring equipment to the region. Deep-sea probes, pressure sensors, and autonomous underwater vehicles are being used to collect real-time data, but the remoteness of the site makes this an enormous challenge. The truth is, we may not fully understand the danger until the eruption has already begun. And yet, as ominous as this situation appears, there are still forces at play that could change the outcome. Could natural pressure release mechanisms prevent a worst-case scenario? Could this volcano enter a period of slow, sustained activity rather than a sudden explosive event? These are questions that will determine whether we are witnessing a geological event of global significance, or merely a temporary tremor in the depths of the ocean. The pressure building beneath the seafloor is not just a matter of magma movement, it is also deeply influenced by the structural integrity of the surrounding rock. The Earth's crust in this region is already riddled with weaknesses, some of which extend for hundreds of miles along fault lines and tectonic boundaries. These weaknesses act as both pressure release valves and potential points of catastrophic failure. The question now is whether this natural balance can hold, or if it is on the verge of breaking apart in a way that will unleash untold destruction. Recent seismographic readings have revealed an increase in microquakes around the suspected eruption site. These tiny tremors may not be powerful enough to be felt at the surface, but they are often a clear indicator that magma is on the move. When molten rock forces its way through the Earth's crust, it creates fractures, triggering seismic activity as the surrounding rock shifts to accommodate the pressure. If these fractures grow large enough, they could act as channels for an eventual eruption, directing the energy toward the weakest points in the volcanic structure. And this brings us to one of the most alarming aspects of this situation. Scientists have identified a massive undersea fracture zone running directly beneath the volcano. This fracture, previously thought to be geologically stable, is now showing signs of stress. The concern is that if the volcano erupts with enough force, it could destabilize this fault, setting off a chain reaction that extends far beyond the immediate vicinity. We have seen similar events occur before, albeit on a smaller scale. In 2018, the eruption of Anak Krakatau in Indonesia triggered a massive underwater landslide. The sudden collapse of the volcano's flank displaced enormous volumes of water, generating a tsunami that struck nearby coastlines with little warning. Hundreds of lives were lost in an instant. The terrifying reality is that a much larger version of this event could be unfolding now. The instability of the seafloor means that this underwater volcano does not need to erupt at full force to cause devastation. Even a partial collapse of its structure could displace enough water to generate waves hundreds of feet high. These waves would not be limited to the immediate region but could travel across entire ocean basins, gathering momentum as they go. Coastal cities thousands of miles away might have only hours to prepare, or in some cases, mere minutes. One of the most chilling aspects of this potential disaster is how difficult it is to predict with absolute certainty. Unlike traditional tsunamis caused by earthquakes, which can often be detected minutes or even hours in advance, the nature of an underwater volcanic collapse makes early warning systems far less effective. The event could occur suddenly, without clear precursors, giving little time for evacuation. What makes this even more concerning is that some of the world's most densely populated coastlines lie within the path of a possible tsunami. The Atlantic Ocean, in particular, is bordered by major metropolitan areas, including New York, Miami, Rio de Janeiro, and Lisbon. If a massive displacement of water were to occur, these cities could face the full force of the waves, with infrastructure and emergency response systems completely overwhelmed. At the same time, the effects would not be limited to land. The shockwaves from a violent undersea eruption could disrupt ocean currents and marine ecosystems on a global scale. The energy released into the water column could trigger sudden temperature shifts, altering weather patterns and causing extreme climatic events in unexpected places. Furthermore, there is the risk of a secondary disaster, an event so rare and unpredictable that it has only been theorized in scientific circles. If the eruption is violent enough, it could send billions of tons of gas-laden water shooting into the atmosphere, temporarily altering the composition of the air itself. This sudden release of steam, sulfur dioxide, and volcanic ash could create a localized cooling effect, similar to what was observed after the eruption of Mount Pinatubo in 1991. Pinatubo's eruption was so intense that it injected aerosols into the stratosphere, reducing global temperatures for nearly 2 years. If a similar event were to occur in the ocean, the cooling effects could be even more unpredictable, as they would be interacting with complex atmospheric and oceanic systems. Some scientists theorize that a sudden release of volcanic gases from the ocean could even trigger abnormal weather events across entire continents. While these scenarios may seem extreme, they are within the realm of possibility. The simple truth is that we are dealing with an event of an unprecedented scale. The forces at play beneath the ocean floor are immense, and the consequences of an eruption could extend far beyond what we can currently predict. As scientists scramble to monitor the situation, they are faced with an uncomfortable reality. There is only so much we can do to prepare. The ocean is vast and unpredictable, and when the Earth decides to unleash its fury, humanity is often left as a spectator to forces far beyond our control. The second major factor that could be contributing to the sudden awakening of this underwater volcano is a phenomenon that has been quietly unfolding beneath the ocean floor for years: deep-sea mantle plumes. These colossal upwellings of molten rock originate from deep within the Earth's mantle, sometimes stretching thousands of miles beneath the surface before breaching the crust. Unlike typical volcanic activity driven by plate tectonics, mantle plumes are independent, rising in a slow, unstoppable surge that can create massive geological upheaval. One of the best documented examples of a mantle plume at work is the one beneath Iceland. This deep, superheated column of molten rock fuels the region's extreme volcanic activity, continuously reshaping the landscape with powerful eruptions and lava flows. But what if a similar, even more powerful process is happening beneath the Atlantic, right under our unsuspecting underwater volcano? Recent geophysical surveys have detected anomalies beneath the ocean floor, zones of significantly higher temperature and density deep within the Earth's mantle. These could be indications that a previously unknown plume is rising, feeding the magma chamber of the underwater volcano. Unlike typical tectonic movements, which tend to be gradual, mantle plumes can accelerate rapidly under the right conditions. If this one is beginning to surge upward, it could drastically increase the pressure in the magma chamber, turning a stable system into a ticking time bomb. The terrifying thing about mantle plumes is that they don't just cause eruptions. They can fundamentally reshape entire regions. The Hawaiian Islands, for instance, were all created by the relentless activity of a mantle plume. Each new eruption adds layers of volcanic rock, gradually building up colossal landmasses where there was once nothing but open ocean. But in the case of our underwater volcano, the consequences of such a process could be far more catastrophic. If a mantle plume is actively feeding this volcano, it could supercharge the eruption, releasing a relentless surge of magma that continues for months, or even years. This kind of prolonged activity could have far-reaching consequences. First, it would significantly increase the likelihood of structural collapse. The sheer weight of newly deposited volcanic material could cause parts of the seafloor to buckle under the strain, triggering massive underwater landslides. As we've seen in past events, these collapses are some of the most dangerous aspects of deep-sea eruptions, capable of displacing enough water to create devastating tsunamis. But there's another, more insidious risk that comes with mantle plume-driven eruptions: massive releases of toxic gases into the ocean and atmosphere. When magma interacts with seawater, it creates a violent reaction, generating huge amounts of steam laced with sulfur dioxide, carbon dioxide, and even hydrogen sulfide. In small amounts, these gases dissipate harmlessly into the environment. But in the event of a large-scale eruption, the sheer volume of gas released could have global consequences. We have seen similar scenarios play out before. The Loki eruption in Iceland in 1783, which was fueled by the Icelandic mantle plume, released so much sulfur dioxide that it triggered a volcanic winter, lowering temperatures across the northern hemisphere. The toxic fumes poisoned crops and livestock, leading to widespread famine in Europe. If our underwater volcano were to experience a prolonged eruption, the consequences could be even more severe. Unlike Iceland, which is an isolated landmass, this event would take place beneath the ocean, where gas emissions could interact with seawater in unpredictable ways. One of the most alarming possibilities is that a massive outgassing event could disrupt the delicate balance of oceanic oxygen levels. Volcanic gases, particularly sulfur dioxide and carbon dioxide, can acidify seawater, leading to the mass death of marine life. Entire ecosystems could collapse, triggering a cascade of environmental disasters. Coral reefs, already under stress from climate change, could be wiped out. Fisheries that support millions of people around the world could be devastated. And in the worst-case scenario, a massive release of methane, another potential consequence of underwater eruptions, could even exacerbate global warming, leading to climate shifts we are wholly unprepared for. And yet, this might not even be the worst-case scenario. If the eruption is violent enough, it could punch through the ocean surface, creating a new island or reshaping existing coastlines. But such an event wouldn't just be a spectacle, it would be an unparalleled disaster. The sudden formation of new landmasses in an active volcanic zone has the potential to generate shockwaves through the ocean, disturbing everything from undersea fiber optic cables to global shipping routes. The consequences would ripple outward, disrupting economies, communication networks, and global trade. This mantle plume hypothesis is gaining traction among some geologists, who point to unusual heat signatures detected near the volcanic region. But the problem is, we don't yet have the technology to fully map and analyze what is happening miles beneath the ocean floor. The deeper we look, the more questions arise. If a mantle plume is truly feeding this growing disaster, we may be dealing with something far bigger than just an eruption. This could be the beginning of a geological event unlike anything modern civilization has ever witnessed. And the worst part? We may not even be able to stop it. The idea that a mantle plume could be fueling this underwater volcano opens up a Pandora's box of consequences that extend far beyond the immediate eruption. One of the most critical aspects of such an event is the long-term geological transformation it could bring about. When a mantle plume becomes hyperactive, it doesn't just create a single catastrophic eruption, it fundamentally reshapes the landscape over time. If this underwater volcano is being supercharged by an active plume, then the sheer volume of magma being produced is staggering. The heat from the rising molten rock doesn't just fuel eruptions, it also weakens the oceanic crust around it. Over time, this weakening can lead to the formation of rifts and fissures on the seafloor, which in turn allows even more magma to rise. This cycle can continue for centuries, creating a permanent volcanic hot zone in the Atlantic. We've seen similar things happen before. The Hawaiian Islands exist because of a mantle plume that has been continuously erupting for millions of years. But the situation in the Atlantic is far more dangerous. Instead of forming an isolated chain of islands, the volcanic activity here could destabilize the entire surrounding region. Underwater volcanic ridges, tectonic fault lines, and sediment deposits could all be affected, creating an unpredictable domino effect. One of the most immediate threats posed by a plume-fed eruption is the risk of hydrothermal explosions. When superheated magma comes into contact with seawater, it creates extreme pressure buildup beneath the ocean floor. Eventually, this pressure has to escape, and when it does, it results in a violent detonation. These kinds of explosions are not only powerful, but they can also trigger tsunamis, underwater landslides, and even secondary eruptions in nearby volcanic systems. In 2019, a similar phenomenon was observed in the Pacific Ocean, when the Kavachi underwater volcano experienced a sudden burst of hydrothermal activity. The explosion sent superheated steam, ash, and molten rock shooting up through the water column, creating a localized tsunami that affected marine life for miles. If our Atlantic volcano follows the same pattern, but on a much larger scale, it could generate a shockwave powerful enough to disturb ocean currents and impact weather patterns worldwide. And the risks don't stop there. The plume could also alter the chemistry of the ocean itself. When massive amounts of volcanic material are released into the water, they trigger a reaction known as ocean acidification. This process occurs when sulfur dioxide, carbon dioxide, and other volcanic gases dissolve into seawater, lowering its pH levels. If the eruption continues for an extended period, it could create a dead zone, a vast stretch of ocean where marine life cannot survive. The consequences of this would be devastating. Fish populations could collapse, disrupting entire ecosystems and threatening the global fishing industry. Coral reefs, already at risk from climate change, could face accelerated bleaching events, leading to widespread destruction of marine habitats. Even deep-sea creatures that have adapted to extreme environments might not be able to withstand the sudden change in water chemistry. And then there's the possibility of something even more catastrophic: a large-scale caldera collapse. If the magma chamber beneath the volcano becomes too pressurized, it could cause the entire structure to cave in. This would release an unimaginable amount of energy, potentially triggering a super-eruption. Unlike typical volcanic eruptions, super-eruptions eject hundreds of cubic kilometers of ash, gas, and debris into the ocean and atmosphere. The resulting tsunami could reach coastal cities thousands of miles away, while the ash cloud could disrupt global air travel and even affect climate patterns. The last time Earth experienced a true super-eruption was over 70,000 years ago, when the Toba volcano in Indonesia erupted. The resulting climate shift was so extreme that some scientists believe it nearly wiped out early human populations. If a similarly massive eruption were to occur in the Atlantic, it wouldn't just be a regional disaster, it would be a global crisis. But the scariest part? Scientists may not be able to predict exactly when, or if, this will happen. Unlike land-based volcanoes, which can be closely monitored, underwater eruptions are much harder to track. The signals they produce, seismic tremors, gas emissions, and heat anomalies, are often difficult to detect beneath miles of water. By the time an eruption becomes visible on the ocean's surface, it could already be too late. If this mantle plume continues feeding the underwater volcano at an accelerated rate, the long-term consequences could extend far beyond just a single catastrophic eruption. The geological transformations that occur as a result of prolonged plume activity have the potential to reshape entire oceanic regions, affecting both the physical landscape and the delicate balance of marine ecosystems. One of the most concerning possibilities is the formation of an entirely new volcanic island. While this might sound like a slow and gradual process, there is precedent for such events happening at a much faster rate than expected. Take, for example, the island of Surtsey, which emerged off the coast of Iceland in 1963 due to an underwater eruption. In just a few years, what was once an unstable, bubbling seafloor had transformed into a solid landmass. But the situation in the Atlantic, if the current plume activity continues, could be far more dramatic. Imagine an eruption so violent that it spews enough volcanic material to breach the ocean's surface in a matter of weeks rather than years. The sudden displacement of water would create a rapid and chaotic rise in sea level around the eruption site, generating tsunami waves before any solid landmass even forms. The newly exposed island wouldn't just be a barren rock, it could be a volatile, unstable landform, constantly reshaped by explosive activity, toxic gas emissions, and frequent seismic disturbances. But the real danger isn't in the formation of a new island itself, it's in what this signals about the deeper activity beneath the ocean floor. The presence of a persistent mantle plume means that magma is rising unchecked, continuously feeding the volcanic system. This could set off a chain reaction that extends beyond the eruption site, triggering seismic instability across a much wider region. Consider the Mid-Atlantic Ridge, the massive underwater mountain range that acts as a boundary between tectonic plates. If the volcanic activity intensifies near this ridge, it could weaken the structural integrity of the seafloor, leading to underwater fissures, landslides, and even partial collapses of the ridge itself. This is where the situation becomes even more terrifying, because if a major portion of the seafloor were to suddenly collapse, it would create one of the largest displacement events in recorded history. Seafloor collapses are rare but devastating. One of the best examples is the Storegga Slide, a massive underwater landslide that occurred off the coast of Norway around 8,000 years ago. This event displaced an enormous amount of sediment, triggering a tsunami that devastated coastlines as far away as Scotland. If something similar were to occur as a result of the mantle plume destabilizing the Atlantic seafloor, the impact could be felt across multiple continents. And here's where things get even worse. If the seafloor collapse coincides with an active eruption, the sudden release of pressure could result in a violent phreatomagmatic explosion. This type of explosion occurs when magma rapidly interacts with water, creating a massive, steam-driven detonation. The energy released would be powerful enough to send shockwaves through the ocean, potentially disturbing nearby tectonic fault lines. Could this trigger further seismic activity along the Atlantic seaboard? It's entirely possible. The strain induced by such an event could place additional stress on major fault lines, including those near the Caribbean and even parts of the U.S. East Coast. Cities like New York, Boston, and Miami, places not typically associated with major earthquake activity, could suddenly find themselves dealing with unexpected tremors and infrastructure failures. Beyond the immediate devastation, the long-term effects of this kind of event could ripple across the globe. If enough volcanic ash and sulfur dioxide enter the atmosphere, it could lead to a temporary but significant cooling effect on the planet. We saw this happen with the 1815 eruption of Mount Tambora, which led to the infamous year without a summer, a period of extreme weather disruptions, crop failures, and food shortages. If a major underwater eruption injects enough material into the atmosphere, the resulting climate shift could impact agriculture, ecosystems, and weather patterns worldwide. The frightening part of all this is that, despite our advancements in geological science, underwater volcanoes remain some of the least understood and hardest to monitor geological phenomena. Most of what we know comes from indirect observations, thermal imaging from satellites, deep-sea sonar scans, and data from a limited number of ocean floor seismometers. But if a plume-driven eruption is happening right now in the Atlantic, there's a strong possibility that by the time scientists detect the full extent of the activity, it will already be too late to prevent the consequences. Another equally alarming cause behind this awakening underwater volcano could be the result of a phenomenon known as deep-sea subduction stress. While tectonic movement is a well-known driver of volcanic activity, there is a lesser discussed but highly dangerous process that occurs when the immense pressures of the oceanic crust force magma chambers to become unstable, leading to unpredictable and often explosive eruptions. To understand why this is happening, we need to look at the interplay between subduction zones and magma reservoirs hidden beneath the sea floor. The Earth's crust is constantly shifting due to the movement of tectonic plates, but in certain regions, one plate is being forced beneath another in a process called subduction. Over time, as the plate sinks deeper, it begins to melt due to the intense heat and pressure inside the Earth. This melting forms pockets of magma that eventually rise back up toward the surface. Most of the time, this process occurs over millions of years, but sometimes, under the right conditions, it can accelerate suddenly and dramatically. The Atlantic Ocean has long been considered a relatively stable tectonic region compared to areas like the Pacific's Ring of Fire, but recent seismic readings suggest that deep beneath the ocean, there may be hidden subduction processes at work. Researchers have detected an unusual increase in deep tremors, small, almost imperceptible earthquakes that occur in the lower portions of the oceanic crust. These tremors, while not dangerous on their own, are often precursors to much larger seismic shifts. This suggests that, far below the surface, portions of the Atlantic plate might be sinking at a faster rate than expected, dragging enormous amounts of rock and sediment downward. As the material descends, it forces magma to move upwards, putting immense pressure on existing volcanic chambers. When this happens near an active or semi-active underwater volcano, the results can be catastrophic. One of the most unsettling comparisons we can make is to the events leading up to the 1883 eruption of Krakatoa. Prior to its infamous explosion, which remains one of the most devastating volcanic disasters in recorded history, Krakatoa experienced months of deep-seated seismic activity, caused by the shifting of magma beneath the crust. What made Krakatoa so deadly was not just the eruption itself, but the way in which it interacted with surrounding water, triggering massive pyroclastic flows and a tsunami that wiped out entire coastal towns. Now, imagine a similar scenario occurring deep in the Atlantic, except on an even larger scale. If subduction stress is driving magma upwards beneath an underwater volcano, the sheer force of the eruption could displace water so violently that it sends towering waves outward in every direction. Unlike Krakatoa, where the surrounding islands provided some barriers to the spread of the tsunami, an open ocean eruption would allow these waves to travel uninterrupted, gaining speed and power as they move toward populated coastlines. Even more concerning is the fact that, in deep ocean settings, traditional tsunami warning systems may not be fast enough to provide sufficient alerts. While we have sensors placed in many high-risk areas around the Pacific, the Atlantic is far less monitored. That means an eruption of this nature could happen with little to no warning, and by the time the first signs of the tsunami reach coastal communities, it might already be too late for an effective evacuation. But the dangers don't stop at the tsunami threat. If the eruption is powerful enough to breach the ocean's surface, it could also send ash and gases high into the atmosphere, disrupting air travel, weather patterns, and even global temperatures. We've seen this happen before with land-based eruptions, such as the 2010 eruption of Eyjafjallajökull in Iceland, which caused massive flight cancellations across Europe due to the sheer amount of ash clogging the sky. A large-scale underwater eruption could have an even more unpredictable impact, especially if it triggers secondary eruptions along fault lines. One of the biggest unknowns here is how interconnected the Atlantic's volcanic and tectonic systems truly are. While we have extensive data on the Pacific, scientists are only beginning to piece together the complexities of the Atlantic's deep-sea volcano network. If one eruption sets off a domino effect, triggering other undersea volcanoes along the mid-Atlantic ridge, we could be looking at an extended period of geological upheaval. Multiple eruptions over a short period could darken skies for months, disrupt ocean currents, and even affect marine life on a global scale. And what if the stress doesn't just trigger volcanic eruptions, but also large-scale seismic events? Some researchers have theorized that intense magma movement beneath the ocean floor could activate previously unknown fault lines, leading to unexpected earthquakes in areas previously considered low risk. A powerful enough undersea quake could cause instability along the Atlantic coast, potentially impacting major cities like New York, Lisbon, and Rio de Janeiro. What makes all of this so unsettling is that scientists have no real way of stopping it. Unlike hurricanes or other natural disasters that can be somewhat predicted and prepared for, volcanic activity is notoriously difficult to anticipate with absolute certainty. And when dealing with deep-sea subduction stress, we're venturing into even more unpredictable territory. We may not fully understand the scale of what's happening until the first signs of disaster begin appearing at the ocean's surface. As we continue exploring the possibility of deep-sea subduction stress triggering a massive underwater volcanic eruption, it's crucial to understand just how complex and interconnected these geological systems really are. Beneath the ocean's surface, there are hidden tectonic forces that we are only beginning to comprehend fully. Unlike surface-level earthquakes or eruptions that occur within more easily accessible areas, the ocean floor holds untold secrets and a network of pressure points that can cause disturbances that ripple outward in surprising ways. One aspect of this subduction process that's especially alarming is the sheer unpredictability of magma migration deep below the ocean's surface. When magma pockets begin to form and rise, the pressures involved are nothing short of extreme. Under normal circumstances, the magma would be forced upward slowly, pushing through cracks in the Earth's crust until it erupts in controlled bursts or lava flows. However, in the case of subduction zones, where one tectonic plate is slipping beneath another, magma's path to the surface is often obstructed or redirected by the intensity of the pressure and friction from the converging plates. This can result in sudden, explosive activity when the magma eventually finds a weakness or break in the crust. In the Atlantic, this is made even more complicated by the relatively young and still developing geological formations in some regions. Unlike the Pacific, which has undergone billions of years of tectonic activity, parts of the Atlantic Ocean's tectonic plate structures are still forming. This means that the magma beneath this region might not have settled into the more predictable and stable patterns we would expect. So, when subduction stress begins to cause those deep tremors and magma pockets rise toward the surface, the outcome could be far more explosive and catastrophic than we imagine. What we see in the Atlantic could be akin to a pressure cooker effect, where the continual subduction causes an overwhelming buildup of energy that eventually must escape. The magma, under these intense pressures, could lead to violent eruptions, not unlike the sudden release of steam from a boiling kettle. And given the immense volume of water that would need to be displaced by such an eruption, it's not just the immediate volcanic event that would be concerning, it's the aftermath that could prove even more devastating. A violent eruption at the ocean floor could rapidly generate a massive tsunami, as we've seen with previous underwater volcanic eruptions. But this type of eruption, driven by subduction stress, could be much larger than anything we've experienced in recorded history. The eruption itself could displace enough water to create a wave capable of crossing oceans, reaching coastlines thousands of miles away. And since we're talking about an event deep beneath the surface, the tsunami could form faster than current warning systems could detect, leaving coastal populations with little time to prepare. Further complicating this potential disaster is the effect that such volcanic activity could have on surrounding ecosystems. Marine life, particularly around underwater volcanoes, thrives on the nutrients released by the eruptions. But as these eruptions become more frequent or violent, there's the risk of completely disrupting the delicate balance of oceanic ecosystems. The sudden shifts in temperature and acidity in the surrounding water, caused by ash and gases released during the eruption, could have catastrophic effects on marine life. We've seen instances of ocean acidification due to volcanic eruptions in the past, but the scale of such an event in the Atlantic Ocean would be unprecedented. Not only could this damage aquatic ecosystems, but it could also disrupt fishing industries and marine-based economies around the world. As these tectonic movements continue, the ability of the ocean floor to handle the pressure and magma buildup could decrease, allowing for more frequent eruptions and seismic activity in a vicious cycle. Once the process starts, it's hard to stop. The cascading effects of one eruption triggering another, combined with the uncharted fault lines and magma systems beneath the Atlantic, could make this much more than just a localized event. It could trigger a global series of geological upheavals that affect everything from local ecosystems to international economies. But the fear doesn't end there. There's the possibility that this deep-sea subduction stress could also result in the formation of a new volcanic island chain. Throughout history, underwater volcanoes have often created new islands that emerge from the sea. These islands, like the ones we've seen in the Pacific, are often born from violent eruptions that change the landscape and add new landmasses to the world. While this may sound intriguing, the process is far from harmless. In fact, the rapid formation of islands due to volcanic eruptions can cause dangerous shifts in ocean currents, leading to unpredictable weather patterns and further disruptions to marine navigation. Let's not forget about the impact on human civilization. As we've seen in events like the eruption of the Hunga Tonga Hunga Hapai volcano in 2022, the sudden eruption of an underwater volcano can have global consequences. Ash clouds that reach into the stratosphere can affect air travel, disrupt global trade, and even alter weather patterns for years to come. If an eruption in the Atlantic were to generate a similar level of ash and gases, the effects could be far-reaching, affecting everything from agriculture to international markets. Moreover, the deeper we go into the causes of these potential eruptions, the more we realize how interconnected the Earth's systems truly are. While subduction stress is a significant factor, it doesn't operate in isolation. The triggers for such catastrophic events are rarely just one single force. They are the result of a complex web of geological, hydrological, and atmospheric interactions that can't be fully predicted. When one force pushes, others will respond, often in surprising ways. Given the potential magnitude of such an event, it's clear that we're standing at the edge of an unknown geological frontier. While scientists continue to monitor deep-sea volcanoes in the Atlantic, there's still much that remains hidden from view. We can only speculate on the magnitude of damage that could result from the combined effects of subduction stress, volcanic eruptions, and the cascading impact on the environment and human life. The awakening of a massive underwater volcano is not just a localized event, it's a reminder that the Earth is constantly shifting, and we must remain vigilant in understanding the forces that shape our world. As we've explored earlier, a massive underwater volcanic eruption isn't just about molten lava spilling into the ocean, it's about the violent forces beneath the surface that could shake the very foundations of the Earth, unleashing devastation that reaches far beyond the ocean depths. To understand the true power of these events, we need to break down how an eruption like this would displace enough water to create waves so colossal they could wipe out entire coastlines and reshape the world as we know it. First, let's talk about what happens when an underwater volcano erupts. Imagine a volcano that's been building up pressure beneath the ocean for centuries. Suddenly, it erupts with the force of 1,000 nuclear bombs, ejecting a tremendous amount of volcanic ash and debris. The real issue isn't just the eruption itself, though. It's the massive upheaval of the ocean floor that can occur during such an explosion. Picture the ocean floor shifting dramatically, causing entire sections to move upward or sideways in an instant. This violent movement displaces massive amounts of water in a fraction of a second. The sheer force of this displacement generates a tsunami, a massive wave that travels outward at incredibly fast speeds, with the potential to reach far-flung coasts before anyone has a chance to react. Now, let's connect this to the terrifying prospect of a mega-tsunami. Most tsunamis are triggered by earthquakes, but underwater volcanic eruptions have the potential to generate waves of an even greater magnitude. These mega-tsunamis are different from the ones we're familiar with from typical storms or earthquakes. We're not talking about waves that just reach the shoreline with a mighty crash. We're talking about towering walls of water, hundreds of feet high, moving at incredible speeds across the ocean. As an underwater volcano erupts, the energy it releases is so immense that it can send shockwaves of water cascading outward. This results in massive waves that don't just crash onto shore but surge inland, sweeping away everything in their path with overwhelming force. When these waves hit coastal cities, the damage is catastrophic. The initial surge can reach heights that are difficult to comprehend, 100 feet or more, smashing through infrastructure, flooding entire cities, and leaving nothing but devastation in its wake. What makes this even more terrifying is the fact that the first wave is often not the last. Tsunamis are a series of waves, and after the first massive wall of water hits, smaller but still deadly waves follow in quick succession, amplifying the destruction. Take, for example, the 1883 eruption of Krakatoa. While it wasn't an underwater eruption, the sheer scale of the eruption and its impact on surrounding waters gives us a hint at what could happen with an underwater volcano. The Krakatoa eruption triggered tsunamis that reached heights of 40 meters, 130 feet, devastating coastal towns around the Sunda Strait in Indonesia and killing over 36,000 people. Now, imagine if a similar event occurred in the Atlantic or somewhere else in the world's oceans, but this time, the eruption came from deep underwater, sending far-reaching waves across continents. The consequences could be far worse, as today's coastal cities are far more densely populated than they were in the late 1800s. But why are these waves so different from regular ocean waves? The answer lies in the energy of the water itself. Unlike surface waves, which are typically caused by wind and only affect the upper layers of the ocean, tsunami waves are generated by massive displacement of the water column. This means that the entire depth of the ocean is involved, making these waves much more powerful and capable of traveling across entire ocean basins without losing much energy. Imagine a stone thrown into a pond, ripples spread outward. Now, picture a wave traveling across the entire Atlantic Ocean with the force of an underwater explosion behind it. That's the kind of energy we're talking about when we consider the potential of an underwater volcanic eruption. Now, let's take this one step further. Imagine that an underwater volcano erupts along a major fault line. The forces at play here would be absolutely devastating. The eruption itself might be violent enough to cause massive shifts in the ocean floor, shifts that displace not just a small portion of the water but an enormous amount of it. As this colossal amount of water rushes out, the shockwaves would travel toward coastal areas on the east coast of the United States, Western Europe, or Africa at terrifying speeds. These waves would hit with the force of a freight train, unleashing destruction on a scale that modern infrastructure might not be able to withstand. The speed of these waves is another critical factor. Tsunamis generated by underwater eruptions can travel across the ocean at speeds upwards of 500 miles per hour. To put this into perspective, that's faster than a commercial airplane. So, when an eruption occurs, the waves are not only massive, They're fast, making it incredibly difficult to predict where they'll land or how much time people have to evacuate. Coastal cities that rely on early warning systems would be put at an incredible disadvantage, as a tsunami triggered by a volcanic eruption could reach land before any warnings are given. Let's also talk about the aftermath. A mega-tsunami isn't just about a single wave crashing into a city, it's about the massive destruction that follows. After the waves hit, the coastline could be severely eroded, and vital infrastructure could be destroyed. Ports, airports, and roads would be wiped out, causing economic devastation far beyond the immediate loss of life. Moreover, the environmental impact would be catastrophic. Marine ecosystems could be completely altered, and the long-term damage to coastal environments could take decades, if not centuries, to recover from. Entire species of marine life could be driven to extinction, and the food chain would be severely disrupted. While we don't know exactly when or where such an event could occur, it's clear that the risk is real, and the potential for devastation is enormous. Underwater volcanic eruptions have happened throughout history, and as we continue to monitor the world's oceans, the possibility of a mega-tsunami remains something we cannot ignore. The energy trapped in the depths of the oceans could one day find its way to the surface with a force we can't even begin to comprehend. Now, with that said, we can only speculate on what might happen next. But if one thing is certain, it's that the oceans hold immense power. The potential for a massive underwater eruption remains a looming threat, and as we continue to watch and study these volatile underwater regions, it's crucial to keep our awareness high and our preparations in place for when the inevitable happens. As we know, underwater volcanic eruptions are highly unpredictable and often occur without much warning. When they happen, the forces that are released into the surrounding water are immense. The eruption itself is a catastrophic event, but it's the way in which it disturbs the ocean floor that truly triggers the chain reaction. As we've already explored, when the ocean floor is disturbed suddenly by the eruption, it displaces a tremendous amount of water. This rapid displacement is what forms the tsunami, a force that can surge across vast distances. What's more, if the eruption is coupled with a collapse of the volcano's caldera or an explosion that sends large amounts of debris into the surrounding waters, this can intensify the tsunami, creating waves that are not just massive but also capable of causing widespread devastation. Picture this: an eruption begins deep beneath the surface of the ocean. The force of the explosion is so powerful that it causes a massive section of the ocean floor to sink, sending shockwaves of water across the surface. But this isn't just a simple ripple effect. The energy behind the explosion creates a chain reaction. As the eruption pushes debris and magma upwards, the water displaced by the eruption is forced outward in every direction. What follows is the formation of giant waves so large that they could reach hundreds of feet in height as they grow in size and intensity. In contrast to what we usually think of when we hear tsunami, these mega-tsunamis are not caused by gradual seismic shifts, but rather by the catastrophic displacement of water in a fraction of a second. They are waves generated by an immense and sudden force, which is why they have the potential to be much more destructive than any wave caused by a typical earthquake. Unlike regular tsunamis that usually start off small and grow as they approach the coast, mega-tsunamis arrive with terrifying speed and height, causing massive flooding and destruction across vast coastal regions. Consider the possibility of a major eruption occurring along the Cocos Plate, near the Central America region, or even in the water surrounding the Canary Islands off the coast of Africa. If a massive underwater volcano were to erupt in one of these areas, the resulting tsunami could sweep across the Atlantic with devastating effects. In just hours, entire coastlines could be submerged. The waves would arrive so rapidly that any sort of early warning system would be all but useless. They wouldn't just strike once, they would come in waves, much like the aftermath of a car crash, where the damage continues long after the initial impact. What makes these mega-tsunamis so difficult to prepare for is their unpredictability. Unlike hurricanes or earthquakes, which scientists can track and predict to some extent, underwater volcanic eruptions can happen with little to no warning. Even if we were to detect unusual seismic activity under the ocean or notice an uptick in volcanic activity, it's nearly impossible to determine whether or not the eruption would be strong enough to trigger a mega-tsunami. As a result, scientists are left in a difficult position, trying to predict the unpredictable. The potential damage from these colossal waves is immense. After an eruption, the coastal cities that are caught in the path of the wave would face destruction unlike anything we've seen in recent history. Buildings, roads, bridges, everything would be wiped away. And it wouldn't stop there. The resulting flooding would devastate critical infrastructure, forcing entire regions to rebuild from the ground up. Thousands of people could lose their lives, and entire communities could be displaced. Beyond the immediate loss of life, the long-term effects on economies and ecosystems could be disastrous. The destruction of ports, airports, and transportation routes would cripple trade and the global economy, and the environmental toll would be unfathomable. One of the most chilling aspects of a mega-tsunami is the way it could completely reshape coastal landscapes. After a massive wave surges inland, it doesn't just flood the land, it erodes it. Massive amounts of earth and rock could be washed away, leaving once thriving cities unrecognizable. And then there's the aftermath of the flooding. Large sections of coastlines could be permanently altered, with river deltas and coastal plains washed away or radically changed. This type of devastation isn't just a short-term issue, it's a problem that could take generations to recover from. As we saw with the 2004 Indian Ocean tsunami, the waves that followed an earthquake were fast-moving and ferocious, and they caused destruction on a scale that the world had never seen before. A mega-tsunami caused by an underwater volcano would be exponentially more powerful and destructive, considering the extra force generated by a sudden, massive explosion. The environment, too, would feel the long-lasting consequences. Marine ecosystems could be decimated by the changes in water temperature, salinity, and the sudden influx of debris and ash. This would create a ripple effect in the food chain, not just for aquatic life, but also for the human populations who depend on these resources for their livelihood. And as with the 2004 tsunami, a similar disaster caused by an underwater eruption would require a global response. Nations around the world would have to come together to assist in recovery efforts, both to provide humanitarian aid and to help rebuild the destroyed infrastructure. Countries with coastlines in the Atlantic, Pacific, and Indian Oceans would have to enhance their preparedness plans and infrastructure to respond to these new threats. As we look to the future, scientists and oceanographers are constantly working to develop better monitoring systems to detect early signs of such catastrophic events. Advances in technology, such as satellite imagery and improved seismic detection, could help identify underwater volcanic activity before it reaches critical levels. Still, the true scale of destruction caused by a mega-tsunami is something that even modern technology struggles to predict and prepare for. Now that we've explored the potential catastrophic consequences of an underwater volcanic eruption and the mega-tsunami that could follow, let's turn our attention to what can actually be done to prevent, or at least mitigate, the impact of such a disaster. It's easy to feel helpless when faced with something as destructive as a mega-tsunami, but the truth is that there are several proactive measures we can take, some within our control, and others that involve advancing our scientific understanding and technology. First, it's important to recognize that prevention in the traditional sense, stopping the eruption itself, is, unfortunately, not something we can control. Earth's natural processes are too vast and powerful for us to halt. However, this doesn't mean that we're entirely powerless. While we can't stop the eruption, we can put systems in place that help us detect the early signs of volcanic activity, monitor oceanic movements, and prepare our coastal populations for the worst-case scenario. One of the most effective ways to reduce the risk of destruction from a mega-tsunami is through early detection systems. Scientists have made great strides in seismic monitoring, and we already have a network of seismographs around the world that detect the faintest tremors under the ocean floor. These seismic sensors can pick up on volcanic activity long before it reaches dangerous levels, providing valuable time to warn the public and take precautionary measures. The earlier we detect potential eruptions, the sooner we can evacuate vulnerable areas and implement emergency response protocols. But it's not just the volcanic eruption we need to track. It's also the movement of the ocean itself. Tsunami detection systems, like the ones already in place in the Pacific Ocean, use ocean buoys and pressure sensors to detect rapid changes in sea level. If an underwater eruption or earthquake causes a significant shift in water levels, these systems can send out an alert to coastal regions, giving them a brief window to prepare. For instance, during the 2004 Indian Ocean tsunami, the absence of an effective warning system contributed to the staggering loss of life. With improved tsunami detection infrastructure, we would have a much greater chance of saving lives and minimizing damage. Aside from monitoring, the construction of tsunami-resistant infrastructure is another critical area of focus. Coastal cities and towns, especially those that lie near active volcanic regions, can significantly reduce the impact of a mega-tsunami by implementing more resilient buildings and infrastructures. Elevated structures, reinforced seawalls, and strategically placed flood barriers can prevent water from flooding inland areas and provide critical shelter to those who need it most. Additionally, using building materials designed to withstand the impact of high waves and intense flooding can help protect human lives and minimize the economic costs of destruction. Evacuation plans are another vital aspect of preparation. While we can't stop a tsunami from coming, we can ensure that people know what to do and where to go when disaster strikes. Educating coastal populations about evacuation routes, creating easily accessible shelters, and holding regular drills could save countless lives. We've seen how quickly a tsunami can strike, and the key to survival is getting out of the danger zone as fast as possible. By creating and practicing well-coordinated evacuation systems, we make sure that when the worst happens, communities are ready to respond quickly and efficiently. Technology will also play a crucial role in advancing our ability to predict volcanic eruptions and the potential for mega-tsunamis. Recently, advancements in satellite imaging have made it possible to monitor changes in the Earth's crust with a level of detail previously thought impossible. By using satellites to track the slightest movements in the ocean floor, scientists can detect early shifts in volcanic activity that may signal an impending eruption. This real-time data can then be used to predict the potential for a tsunami, giving authorities time to issue warnings and evacuate coastal populations. Another area where we're making progress is in the field of geoengineering, specifically in the development of ways to potentially reduce the severity of natural disasters. Some experts have proposed the idea of using underwater structures to dissipate the energy created by a volcanic eruption before it has the chance to displace large amounts of water. For example, placing energy-absorbing materials or large, strategically placed barriers around the eruption zone could help reduce the size of the waves that are generated. While this is still highly experimental and not yet a viable solution, it demonstrates how technological innovation might one day offer a new way to mitigate the effects of these devastating events. There's also ongoing research into volcanic eruption prediction models, which take into account various factors such as gas emissions, changes in the shape of the volcano, and seismic activity to forecast eruptions. These models could provide more reliable predictions and give authorities more time to act. In recent years, scientists have seen increased success in predicting eruptions in regions like Iceland and Indonesia, thanks to these advanced models. The goal now is to refine these models to a point where they can be applied to underwater volcanoes with equal effectiveness. Furthermore, enhancing our global cooperation is crucial. Natural disasters like a mega-tsunami caused by an underwater volcano aren't confined by national borders, and the aftermath can affect entire regions, even the world. Countries must collaborate to share data, resources, and strategies for disaster preparedness. This means creating international monitoring networks, sharing early warning systems, and ensuring that aid and assistance can flow freely when disaster strikes. The global response to major earthquakes and tsunamis has improved in recent years, and if we continue to work together, we will be better equipped to face future challenges. Lastly, in order to create lasting change, public awareness and education about the risks of mega-tsunamis and other natural disasters are paramount. While governments and scientists can do their part in preparing for these events, it is ultimately the people who will need to act when disaster strikes. Ensuring that communities understand the threats they face and know what steps to take in case of an emergency could be the difference between life and death. Schools, media outlets, and local governments should continue to promote preparedness, ensuring that everyone is ready to respond to a crisis. As we continue to explore the frontiers of science and technology, the hope is that, one day, we'll have a more comprehensive system in place to prevent, or at least reduce the impact of a mega-tsunami. Until then, we must remain vigilant, prepared, and united in our efforts to safeguard coastal populations from the devastating effects of underwater volcanic eruptions and the tsunamis that they can unleash. With ongoing advancements in science and technology, and a more proactive approach to disaster preparedness, we stand a better chance of surviving and even mitigating the next big one. Continuing on this topic, it's important to further explore the evolving relationship between technological innovation and disaster preparedness. As we develop more robust systems for monitoring and responding to underwater volcanic eruptions, we also need to consider how we can better integrate artificial intelligence, AI, and machine learning into these processes to refine our predictions and responses even further. One key area where AI can significantly enhance our tsunami prediction capabilities is through predictive modeling. By analyzing vast amounts of data from seismographs, oceanic sensors, satellite imagery, and historical records, AI algorithms can be trained to detect patterns that may not be immediately visible to human analysts. For example, AI could help identify subtle changes in seismic activity that precede major volcanic eruptions or tsunami-triggering events. These predictive models could work in tandem with traditional methods, offering real-time alerts with greater accuracy and reliability. In turn, this would allow authorities to take even more timely and targeted action, such as evacuating at-risk areas and mobilizing emergency resources. Furthermore, real-time data sharing and communication networks could be significantly improved by harnessing AI technology. In a large-scale disaster, the ability to quickly process and share information across various platforms, governments, emergency services, humanitarian organizations, and affected communities becomes crucial. AI-driven systems could facilitate the faster dissemination of warnings, helping to streamline communication between different entities and enabling a more coordinated response. Imagine an automated system that not only detects an underwater eruption but immediately generates and disseminates a warning message to coastal areas at risk, along with evacuation instructions and alerts to first responders. Additionally, as our understanding of climate change continues to evolve, there's an increasing recognition of the interconnectedness between environmental shifts and volcanic activity. While climate change itself is not directly responsible for triggering volcanic eruptions, it does play a role in how the Earth's crust behaves. Melting glaciers, rising sea levels, and increasing pressure on tectonic plates could, over time, contribute to the activation of dormant volcanic systems. As climate change progresses, it's possible that regions previously thought to be low risk could face new threats, and underwater volcanoes in certain areas may become more volatile. To prevent a disaster of this nature, monitoring systems must be adaptive and able to incorporate environmental changes that influence tectonic activity. Scientists must continue to closely monitor these environmental indicators, and proactive measures should be developed to account for the unpredictable effects of a rapidly changing climate. Meanwhile, on the ground, community preparedness remains an essential piece of the puzzle. As we've discussed before, warning systems can only go so far if the affected population doesn't know how to react. That's why local education and training efforts are crucial. In regions with the highest risk of tsunami-triggering volcanic eruptions, schools, local governments, and community organizations should work together to provide regular training and drills. Citizens must know how to identify the warning signs of a potential tsunami, such as unusual seismic activity, a rapid retreat of the ocean, or sudden changes in the atmosphere. Additionally, local authorities should invest in evacuation infrastructure, such as elevated walkways, emergency shelters, and well-marked routes, that allow people to move to higher ground quickly in the event of a tsunami. These measures are especially vital in remote or rural coastal areas that may be the most vulnerable when disaster strikes. Coastal city planning also plays a vital role in mitigating the effects of potential tsunamis. For example, urban development should be carefully managed in tsunami-prone regions to ensure that buildings are constructed with resilience in mind. Governments should incentivize the use of tsunami-resistant building materials and the design of structures that can withstand not only seismic shocks but also the destructive forces of massive waves. Coastal zones should be carefully mapped and regularly reviewed to understand areas of high vulnerability, and zoning laws should restrict the construction of high-density housing in areas most at risk. This type of proactive urban planning can greatly reduce both human and economic loss in the event of a natural disaster. On a larger scale, international cooperation is crucial to ensuring that the world is prepared for mega-tsunami risks. After all, these catastrophic events often extend far beyond the borders of a single country. In the aftermath of the 2004 Indian Ocean tsunami, global relief efforts proved that the world can come together in the face of tragedy. Governments, non-governmental organizations, NGOs, and private sector companies must work together to share resources, data, and technologies. For example, countries with advanced seismic networks, such as Japan and the United States, could collaborate with developing nations to improve detection systems in at-risk areas. Joint ventures between nations could also help to fund research and develop innovative technologies that can mitigate the impacts of tsunamis, such as underwater barriers or advanced tsunami energy dissipation techniques. In tandem with these global efforts, scientific research into underwater volcanoes and the mechanisms that drive their eruptions will continue to be essential. The more we learn about volcanic activity beneath the ocean, the better equipped we'll be to predict and mitigate the impacts. Universities, research institutions, and governmental agencies around the world must continue to invest in oceanography, seismology, and volcanology to deepen our understanding of these phenomena. Collaborations between scientists from different disciplines can lead to breakthroughs that will improve not only our ability to predict megatsunamis, but also the overall safety of coastal communities in the long run. Ultimately, while there's no way to eliminate the risk of an underwater volcanic eruption triggering a megatsunami, we have the power to reduce its potential impacts significantly. By enhancing early detection systems, strengthening our infrastructure, improving education and training, and fostering international collaboration, we can increase our chances of survival and lessen the destruction that these powerful events can cause. It's about creating a world where, despite the natural hazards we face, we are resilient and prepared for whatever comes next. As we reflect on the potential dangers of a massive underwater volcano awakening and its capacity to trigger a mega-tsunami, it's clear that the implications of such a natural disaster are immense. From the catastrophic loss of life to the widespread destruction of coastal cities, the risks associated with underwater volcanic eruptions cannot be overstated. However, through careful study and preparation, we can begin to understand how these powerful forces of nature work and what steps we can take to minimize their impact. We've discussed various causes that could set off such a catastrophic event. From tectonic shifts deep within the Earth to the effects of climate change influencing volcanic activity, each potential trigger offers us a glimpse into the complexities of our planet's geological systems. The interplay between seismic activity, oceanic conditions, and atmospheric patterns is intricate, and even slight disruptions in one part of the world can set off chain reactions that affect entire regions. Understanding these causes in greater depth allows scientists to create more accurate predictions and better early warning systems that can save lives when the next natural disaster strikes. But prediction alone isn't enough. Technology plays an indispensable role in the modern efforts to prepare for, mitigate, and ultimately survive such disasters. From AI-driven predictive models to seismic monitoring stations placed deep beneath the oceans, technological advancements are giving us the tools we need to stay ahead of potential threats. These tools are only useful if integrated into robust early warning systems and communicated effectively to at-risk populations, enabling authorities to act swiftly and decisively. Local education, community preparedness, and evacuation planning must complement these systems to ensure that people know exactly what to do in the event of an emergency. Furthermore, global collaboration is essential. Countries and organizations around the world must unite to pool resources, share knowledge, and develop innovative solutions to counteract the destructive power of tsunamis and volcanic eruptions. Working together, we can create stronger, more resilient infrastructures that are better able to withstand the ravages of nature. The future of disaster preparedness lies in this cooperative spirit and the ability to respond effectively on an international scale. While we cannot completely prevent a mega-tsunami from occurring, we have the power to reduce its devastating effects significantly. The investment in scientific research, improved early warning systems, and smarter urban planning will increase the safety and security of coastal regions, allowing us to live in greater harmony with the unpredictable forces that shape our planet. We can't control nature, but we can certainly be better prepared for the unexpected, minimizing the destruction and maximizing our chances of survival. Now that we've explored the potential causes, consequences, and solutions surrounding underwater volcanic eruptions and their ability to trigger mega-tsunamis, it's crucial that we continue to raise awareness and stay vigilant in our preparations. We must be proactive, working together across borders to ensure that the most vulnerable communities are ready to face whatever comes next. If you found this information insightful and want to stay informed about the forces shaping our world, don't forget to subscribe. The more knowledge we have, the better prepared we'll be for what's to come. Stay safe, stay informed, and always be ready for the unexpected.